use set notation for this. If you use the soft parentheses, that's a coordinate pair. So if you're going to list a string of things, give me the x's, give me the y's. Is this a function? Yes, because the x's don't repeat. X only occurs once. Okay, domain and range of this guy, is this a function? Yes. Is this a one-to-one? Yes, because the y's don't repeat. Good, because if we take an inverse and we swap the x and y, we interchange them, then the y becomes our new x, and that won't repeat. Okay, see if I can move this up a little. Oh, I thought I had my board working. I just did before you guys walked in here. Did anybody bump into my thing up there? Yeah, do you want to know something funny? Last year, one of the algebra kids was a very big, ninth grade child. And every time he walked by, he would smack the thing.
Definitely so.
Walked by and smack it. And one day, because I was always off after his class, and I came in, and my board was always off. So one day, I came in early, and I had just dropped something off, and so I stayed. And as he's walking out, he gives it a smack. No wonder why this keeps going off on me. Yeah. He was big. He was a big ninth grade kid. He probably still is in ninth grade. He wasn't doing what he was supposed to do. So, all right. So which relations are functions? So we're good with the 1 and the 3? Okay, this one, the x is repeated. Any questions on any of those 3? We do a lot with inverses in here. So we need to make sure we have functions, and then we need to make sure we have inverse functions. These didn't ask for one-to-ones, but God bless you. What values can x not have? It can't repeat anything that's there. So it can't be an 8, it can't be a 34, it can't be a 6. It can be anything else but that. And domain and range. I have the calculators here. I don't have the contact print calculators yet. We're taking inventory to see what calculators we have. But I do have calculators for when you come in and if you need to use them. So any questions on these? Range, be careful on your range. If it helps you, box these off. Make a box here. Just put a box around what you're going. This obviously keeps on going, but this is the lowest you can go. So you're going to start at -3 and go up. The order of this is important. All right, these guys. Very similar to the parabola. Is this a function? Yes. Is this inverse a function? No. No, because that would be a vertical line. Again, these are finite points. These are discrete points. They have specific values. So we can only take out the x's, we can only take out the y's. They're not connected. If we put a line between them, that's different. If we put a line between these guys, what would my domain then be? -4 to 3. And what would my range be? -2 to 2. Good. Okay, again, box the circle in. -2 to +2 for both. Number 13. This is a piecewise function. We do piecewise. I know you guys did piecewise, and I think you even did them in Algebra 1. Common Core in Algebra 1 does piecewise. So just make sure this is a function first. Your domain is covering all real numbers, and your range is stopping right here. Everything down here is covered. And Amanda, you need to go to see Ms. Roman. Hello, Mrs. Moore. Gabby the Daddy? Yes, okay. She said after announcements, and I just remembered. So you need to go down and see Miss Roman. Gabby the Daddy? You need to go see Miss Cass. Let me give you Cass. Okay, so is everybody good with this? All right. So I think here's some more. This is called the step function. A step function is a function because if you follow it down, it goes to here, open, then jumps up and starts there. Open, has an open and a close. That's a step function. Now your domain does use every number, but your range only uses integers. So if you want to say the set of integers as a range, that's fine. But a step function does not have any fractions in it. It goes to the next whole number. Because if you, well, this is going to continue, but you just went from here to here. Okay, if you just went from here to here, it's a continuous step. I see where you're going with that. It would have gone like this. It would keep on going. A step function keeps on going. Kind of like a parabola when you do this, this does keep on going. There's no way to make an arrow. So if you did from there to here, yeah, I see what you did. So if you did from -5 to 3, soft bracket, yeah. Technically a step function just keeps on going this way. But the y values are only integers. And these guys, this, be careful, is open here. So when you're using these values, you're going to stop here at the -1, and then you're going to continue, break it here, continue at the 2 to infinity. The 0 is covered because of this one. The 0 is all by itself. And then it jumps up here and starts again at 2. I don't know where this piece came from. It looks like it belongs somewhere. It doesn't belong here. And this one also is continuous within this. So find your endpoints, box it in. Find your endpoints. If you box it in, it's a little easier to tell. And just watch your open and your close. Good. Domain restrictions. And you're going to see them throughout this because we do a lot with functions. We do a lot with functions throughout the whole pre-calc course. So you're going to see these domain restrictions come up all the time. And one thing we always do when we work with a function is we state our domain, we state our range. So there's only 3 basic ones that you're going to get. A fraction. What can not be in the denominator? 0, because it makes it undefined. So whatever is here, we just set this equal to 0. So this is the restricted part. It is restricted. It cannot use a 0. So our domain, we remove it. If this is my 0, I want to remove this. I still want to be able to use everything else. So my allowable domain under my restrictions, this is something that's not allowed. So my restricted domain, once I remove this, says just get it out of there. And my domain will be everything else but the 0. Again, a fraction, you're going to set this equal to 0. If whether you add 4 and take the square root, or you do your perfect squares, whichever way you like to do this is fine with me. Remember though, if you take the square root, whenever you take the square root, you always get a plus or minus. So remember to include your plus or minus. Now, these are the guys we have to remove from our allowable domain here, from our regular domain. And what's left is all the pieces we need to use for our restricted domain. So we're going to use negative infinity to negative 2. We're going to jump over negative 2, go to 2, 2. We're going to jump over that, and then 2 to infinity. Okay? Anytime you have a denominator, set it equal to 0. Take out the parts out of your all real numbers that you cannot use, and give me your restricted domain. It's restricted to only what's left over. A radical is another restriction. In our set of real numbers, we cannot have a negative under a radical sign. The radicals build a lot easier. Take whatever's under your radical and just set it greater than or equal to 0. Because on your number line, you can use a 0. You can't use any negatives. So you can use from here to here. So just take whatever under there, that argument, and set it greater than or equal to 0. So our domain would be from 0 to infinity. Can't use a negative underneath your radical sign. We assume all real numbers, except for when we get to that one little step when we do the parabolas and we find the roots, and the roots are imaginary. That's the only time we're going to throw an imaginary number at you guys. Everything else is in the realm of real numbers. Same thing here. This is nice because it actually builds your domain. Greater than or equal to 0. It can't be negative, so solve. X has to be greater than or equal to negative 3. So your domain, and I'm allowed to have a 0 under my square root. Square root of 0 is 0. Good. And the last one kind of combines the both of these. It combines a radical and a denominator. So now we have two types of restrictions. 1, a radical cannot have a negative. 2, a denominator cannot have a 0. So therefore, we're just going to take this out and set it greater than 0. In my number line, I'm not allowed to have a 0, not allowed to have any negatives. So I can be from here to here. So just set it greater than 0. So now this domain says 0 to infinity. Got it? It's just combining the two restrictions together. This one, same process. Just set it greater than 0. Cannot be equal to 0. Negative 3 to infinity. Good. Okay. 3 basic domain restrictions. They're going to follow us everywhere. What's the domain restriction for this? What's the domain for this? One, I can use 1. Can I use a 0? Can I put a 0 in here for x? Yeah. Can I put a negative 1 in there? Yeah. So now, if I took this and I said, okay, has to be, if it's equal to 0, can't use it. If I do this, this does not exist. So this has no domain restriction in our real number world, in our real number sense, which is what we use. Any number I put in here is going to square this. So I can't find a negative 1 to make that 0. Okay. A radical. Any fourth root, sixth root, eighth root, any even root is going to have a domain restriction. It can't be any negative number, right? For anything. Can I do this? No. Can I do this? So that's 2, right? So I can't say negative 2 times negative 2 times negative 2 times negative 2. It will always be positive because they'll pair up. So all the evens pair. Can I do this? What's the cube root of 8? 2. So there's an invisible line here that I just keep hitting. So 2 times 2 times 2. What about negative 2 times negative 2 times negative 2? Negative 8. So I can take an odd root of a negative number. So my odd roots have no domain restriction. My even roots will have domain restrictions. I can't have negatives. All my even roots will work the same as my regular square root does. Same way. Take them out, set them greater than or equal to 0, or if they're in a denominator, greater than 0. My odd roots have no domain restrictions. Okay, because the 3 odds give me that negative. Just a little food for thought there. Okay, and this, I don't think we have this. Some of these are big. Xerox is different. Alright. So this is still kind of a little review. Number systems, equations, all your favorite things, fractions. Do you also hate factoring as much as you hate fractions? Oh, phew. Phew. Factoring and fractions are like, everybody's always moaning at me. Good. Factoring is good. Okay. So, now, depending on which set of numbers, and again, we're going to assume real unless they specifically say so. So if you're looking for a solution for your equation, we're going to take the square root, and we always reduce our radicals just like we did in Algebra 2. If it can be reduced, we reduce them. We reduce all fractions. The one thing you do not have to do in pre-calc is rationalize a denominator. In other words, when you get this in Algebra 2, could you leave that? No. So you had to multiply by radical 3. Right? The one nice part about pre-calc, you no longer have to do this. You can leave your radicals in your denominator. So that's kind of nice. All right, so now, but we still have to reduce everything. Reduce your fractions, that's always understood. It's not going to say it in your problems, but that's understood. Reduce your fractions, reduce your radicals. Okay, so now this guy, in the real numbers, we can use radical 10. That exists in our real numbers. Does it exist in our rational numbers? Is radical 10 irrational or rational? Irrational. So this is an irrational number, so in our rational numbers, no solution. In our set of real numbers, plus or minus radical 10. In our set of integers, does it exist in our set of integers? Radical 10? no solution. So mostly we're going to work with real numbers. But every once in a while, we find something that has a root that we can solve the equation, but it really doesn't make sense in our number world. So we call this guy the extraneous root. And whenever you deal with fractions, radicals, you're going to be looking at your extraneous roots. Make sure they check, make sure they work. The nice part about this is we're going to find your domains. So if we find your restricted domain and you go through and work out a problem and it's not part of your allowable domain, can't work, right? So it's an easy way to check. So in this case, this nice little fraction, whoops, you're going to factor everything and you're going to find any domain restrictions. So you've got a denominator. So we're going to set those two things equal to 0. These are two values that you're not going to be able to use for x. So we're going to take them out of your domain. So there's our allowable domain. If you struggle with creating your domain, use a number line. Take these out, write them like this, take them out. Domains are a little tricky in the beginning, but once you start using them enough, you'll catch them. So you can use all of this, you can use all of this, you can use all of this. Think of these as open circles. You just can't use those. And that'll help you write your allowable domain, your restricted domains. Now, to solve your fraction, because this is an equal sign, if it was not an equal sign, if it was an expression, we would have to keep your denominator. But an equal sign, we can multiply through your denominator. If you struggle, find your least common denominator. This guy needs an x minus 2. This guy needs an x plus 2. So we covered both of those in that. If you struggle with reducing your fractions, put your least common denominator on the top of every term in its numerator. Just multiply like this. However you like to do this is fine with me if you have a pattern or some way that you like to do this. If not, multiply every term by that denominator. Now cancel out your common factor. Then you're left with 1 times x plus 2. I'm just going to put the 1 times that. Equals, out comes your x plus 2. You're left with 3 times x minus 2. This uses both. You're left with 6x. Once you do that, you should have no denominators left. And then you solve. So this is x plus 2. Collect your like terms. And solve for x. So if you add 3x and you subtract 2, so x is equal to negative 2. Go back and check your domain. Are we allowed to use negative 2? So is this going to work? Mm-mm. We don't even have to go put it back into our fraction because it was not part of our allowable domain. So this has no solution. All that work to find out no solution. This is your extraneous root. That's your extraneous root. It was a solution for the equation part, but when we put it back into the scenario of the problem, it doesn't work. Good? You guys remember doing all this, right? Remember doing this? Just a little brush up. This first unit is a lot of like review, brushing up on parts. We came up with this unit a while ago so that we figured out where our kids needed a little bit of extra boost. solving an equation with a quadratic type. Quadratic type meaning every once in a while I have a little bit of a problem with this board. It doesn't always like me. Okay, the quadratic type being the ax squared plus bx plus c. Usually I have to quit for some reason and start again. I don't know why. So your quadratic type is your ax squared plus bx plus c. Now, we have a couple of different ways you can do this. Factoring is one way to solve. Whenever you see your x squared, you have the semi-values, get everything to one side. That's a must. Just get everything to one side, set it equal to 0. Okay? If you want, you can do like we did before with the x squared equals 10. Take the square root of both sides. X squared equals 4. You can do the same thing. You could give me your perfect squares. I'm not fussy about that. Whichever one you prefer. God bless you. If all fails and you can't factor, your quadratic formula is good. You guys learn to complete the square. Complete the square is absolutely fine. I didn't throw complete the square in here because I like to kind of do that a little separate, but I know Algebra 2, Common Core does a lot with complete the square. So you guys should be a little bit up to completing the square. So let's see if it's going to let me solve anything here. So if we were going to factor this, so if we're going to factor, what are the factors? It's a trinomial. I can factor this into two binomials. Pretend this had this. What would you factor this into? X minus 2, x minus 1, right? Okay, so now you took the square and you divided that in half, right? So take the 4 and divide that in half. There's your square. So when you do your middle terms, this will all work out. If you FOIL this whole thing out, you'd get your x squared in the middle. Are we good to go? Or can we factor again? We can factor again. If you wanted to set both of these equal to 0, you could absolutely do this here. Take your square root. If you wanted to set this equal to 0, you could certainly do that one too. Or if you wanted to, you could do your perfect squares. This, whichever one you prefer to do, is fine with me. However, just remember, when you take the square root, you get a plus or minus. And what is the square root of 1? 1. Good. So my roots all together, as a set notation, plus or minus 1, plus or minus radical 2. Okay. I don't know if this is going to let me turn this down here. Okay. Points of intersection. If I write something wrong on the board, stop me before I do the whole problem. I tend to look up and down real quick because I'm usually talking in the same time. And sometimes I write them down wrong and I do the whole problem and then somebody will say, oh, that was supposed to be a negative. So stop me. Don't be afraid to stop me. If I write the wrong number while I'm talking, stop me. So, okay, so this is an equation of what? What will I get if I graph this? A line. What will I get if I graph this? Parabola. So a parabola and a line can cross twice, can cross once, it can be tangent to it, or it can have no solution. So other than putting this in my y equals and checking it graphically, I can also do this algebraically. Because they're both the same y values, I could set my y's equal to each other. It's like your substitution. and then solve this way. Can you guys see okay back there?
Yeah.
So we're going to subtract x, subtract 2. And we're going to factors. Give us some factors for this. So what are these factors? It's x squared minus 3x minus 4. X minus 4, x plus 1. Good. So x is equal to 4, and x is equal to negative 1. Are we done? Yeah, is this a point on my graph? We have to find your y value. So plug it back in and find your y value. Okay. Sorry about this board. One of these days I'll figure this out right. Okay, do the rest for homework, guys.